So in Chapter 4, we're going to deal with something called electron configurations. And so what does the word configuration mean? You know what the word configuration means? Configuration means how something is arranged. Okay, to configure something means to move it around or to rearrange it. So configuration means how they are arranged. So when we're looking at electron configuration, we're going to be talking about and describing how electrons are configured or how they are arranged within an atom. Where are electrons located within our atoms? Okay, that's what we're looking at. Where our electrons are located. Okay? So, electron configuration, it tells us the arrangement of electrons in an atom. Okay, we're going to be able to pinpoint where electrons are located. We're going to be able to talk about what energy level or what shell they are from the nucleus. We're going to be able to tell what shape is the orbital that's holding them. We're going to be able to tell a lot of different things just using these electron configuration tools. Okay. So electrons like to assume arrangements with the lowest energy. And so this is like everything in nature, everything that requires energy, which is everything, likes to assume or likes to go to the lowest possible energy level. Okay. Electrons are the same, and I'm going to talk about what these energy levels are here in just a second. But in our electron configurations, we need to basically, what this is telling us is that we fill our electron holders, kind of, I'll say for right now, from the bottom up. Right? We fill them from the bottom up, so that'll make more sense here in just a little bit. Okay, so what these are called is that we're doing ground state electron configuration. So that means we're not talking about electrons that have extra energy. Right now we're not talking about electrons or elements that have a charge. We're just going to find the electron configurations for neutral atoms that are very stable. Okay, they're in their ground state. They're not in what they call an excited state. Okay, and an excited state electron means that they just have more energy and all that stuff. We're not dealing with that. We're dealing with the most basic electron configuration, which is called ground state. Okay, and we're going to learn how to determine the ground state electron configurations for every element. You'll be able to do it for every element following the same basis of rules and using your periodic table. Okay, so within our atom, electrons are housed in something called an orbital. So orbitals are like electron holders, right? They're little pockets that contain our electrons. So the models that you've seen before where the electrons sit on a little ring outside, that's not really what we know today, right? It's not like what you've seen in the pictures. It's not like the Rutherford model where you have your nucleus and then an electron sits here and orbits the nucleus, right? That's not really what happens, okay? And it's not like the Bohr model, which looks like this. We have our nucleus, and then we've got so many electrons on each shell, right? That's not really what the atom looks like today either, okay? So what the atom looks like today is that electrons, or what we know the atom looks like, that it hasn't changed. What we know it looks like today is that atoms are held within these things called orbitals. And orbitals are like electron holders. Okay, that's what an orbital is. Okay, they're electron holders, or sometimes you can call, sometimes I'll call them pockets, right? They kind of rope in the electrons, but still they don't have a little place for them to sit, right? Electrons are constantly in motion. So these orbitals are kind of what contain electrons. And there's 4 different types of orbitals, S, P, D, and F. We don't get into the F orbitals a lot because they are crazy shaped, right? There's all kinds of different configurations for the F orbitals. But the 3 main types you need to know. So an S orbital is a sphere. Okay, so within an atom, you see an s orbital, and the nucleus is found right inside of that, and then there's a sphere directly around there that holds 2 electrons. Okay, so an s orbital holds 2 electrons. Okay, every orbital holds 2 electrons only, but the s orbital holds 2 electrons, and it's shaped like a circle. Okay, so you might want to draw an s orbital as a sphere. Okay, it's a circular shape. So the first 2 electrons in every energy level, the first 2 electrons go here. First 2 electrons in every energy level go here. So with every time we add an energy level, we add a new sphere, right? And then the first 2 electrons in that energy level go there. Okay? Next comes the p orbitals. And p orbitals are shaped kind of like a dumbbell. Okay? P orbitals, each of these pockets hold 1 electron, which means this orbital as itself holds 2, right? So every orbital holds 2 electrons. So this together holds 1 here and 1 here, okay, which gives a total of 2 electrons. All right, so using our orbital shapes, it applies directly to the periodic table to help us determine where electrons are, okay? And so on your periodic table, I want you to label these 2 groups right here. Sorry, I'll put it on this one. These 2 groups, the purple, those are the S, that's the S block. We call it S block. Okay, the blue group is called the P block. Pink is called the D block. And then the lanthanides and the actinides down here are the F block. Okay, so we're going to be able to determine which of these elements contain electrons in each of the blocks. Okay? So, if you look at this S block right here, how many elements are in the S block, right? Per row, how many elements are in the S block? Right? 1, 2. And how many electrons can the S orbital hold? 2. So we move over to the P block per row. 1, 2, 3, 4, 5, 6. How many electrons can the P orbitals hold? 6. How many electrons can the D orbitals hold? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it lines up perfectly for us to determine this, okay? So what we're going to be challenged to do from here on out is we're going to say, if we have an element, like let's say we're looking at carbon. We're looking at carbon. What block of elements is it in? It's in the P block, okay? So when we're looking for the electron configuration for carbon, we want to look at its outermost electron. We're looking at the last electron that gets added to carbon. The very last electron that gets added to carbon. So when we're asked for electron configurations, we're looking for carbon's very last electron added. Okay, so let's think about this. In terms of carbon, how many electrons does a neutral carbon atom have? It has 6, right? Because it has 6 protons. So a neutral carbon atom should have 6 electrons. Do we agree with that part? Okay, so carbon has 6 electrons. So the way we find out where these electrons are located is we just start moving along the periodic table. Okay, carbon's first 2 electrons went filled in the S block. So here, and helium really should sit over here for this demonstration, but it went here. Okay, so they had their first 2 electrons added when in the S orbital, right, in that sphere. Then we jump down a row, and we say the next 2 electrons that got added went in the 2s sphere. Right? We added another energy level, and we add an energy level when we go down the periodic table. Okay? Just listen while I'm doing this, and then we're gonna walk through them together. But I want you to see this. Okay? The next electrons that get added are in what orbital? The p orbitals, right? We're gonna just keep moving to the periodic table until we get to carbon. So that means carbon's outermost electron is in the p orbitals. Okay? And so the way that's written is that it's 2p2. That's its outermost electron. It's in the second energy level, it's in the p block, and it's the second electron to get put in there. Okay? So I'm going to walk through a lot more of these examples with you, but I want you to see, do you have a general idea of how this is coming together? Kind of? Okay, I know it's still a little bit shaky, but we want to see how it's coming together. Okay? So as you go down a row in your periodic table or a period, that means we are adding another shell to our atom. Okay, our atom is expanding outward from the nucleus. So you might want to write that down, right? As we go down in the group, oh man, my things. Okay, as we go down in the periodic table, so as we move down a period, which is the row, on the periodic table, we add an energy level, which is also known as a shell. Okay, so that concept is very similar to the concept of the model of the atom that looks like this, right? Here's our nucleus. We've got first shell of electrons, second shell of electrons, third shell of electrons. That model is similar to this, right? As we increase an energy level, as we move down the periodic table, we're adding a shell. Okay, except it doesn't really look like electrons orbiting on that shell, right? We add a shell, which means we add another s orbital, another p orbital, d orbital. So these things are pretty big, right? We talked about this, the space between the nucleus and the atom would be the ratio of if we had an atom, like in real, like if we blew it up to big size, if the nucleus was the size of a marble, do you remember what the size of the atom would be? The nucleus is the size of a marble. The size of the atom itself would be the football field. So the nucleus is the size of a marble. The atom itself is the size of a football field. So that means those electrons take up a lot of space, right? A lot of it's empty space, but electrons take up a lot of room. So as you increase these shells, you're getting more and more space for these electrons to roam. Does that kind of make sense? So that ratio should give you an idea that the nucleus is so small, but we have a lot of room for electrons. Okay? All right, so we've talked about our... Okay, now I'm going to give you kind of a cheat sheet to help you determine where we go on our periodic table to put these electrons into their configuration. Okay, when we're determining the electron configuration and we write out our electron configurations, I'm gonna just show you an example of carbon again and what your final answer for carbon would be. If I was looking at the electron configuration for carbon, I would say we have to account for all 6 of the electrons. So I say the first electrons fill the 1s2 orbital, right? We said there's another s orbital that goes right here. So the first 2 electrons go in the 1s orbital. The next 2 electrons fill the 2s orbital. The next 2 electrons go in the 2p orbital. Okay, so these numbers should add up to the total number of electrons in carbon, which is 6. Okay, so that's what our final answer for carbon would look like. If I was asking you for the electron configuration for carbon, you're telling me the first 2 electrons go here, the next 2 electrons go here, then we move over and carbon is right here. So the final 2 electrons are located in that 2p orbital. Okay? Is that kind of making sense or is it still a little fuzzy? Still a little fuzzy. Okay, that's okay. All right, we're going to keep trying. We're going to keep working through some. I know this is totally new and it seems totally crazy, but I promise it will work once we start looking at some examples here. Okay, so here's electron configurations for elements 1 through 10. 1 through 10. Okay, hydrogen only has how many electrons? 1. So its only electron is located in the 1s orbital. Okay, because it's in the first energy level. That's where hydrogen is located on your periodic table. It's in the first energy level. Will we agree with that? Hydrogen in the first energy level. It only has 1 electron, so it has to go in that s orbital. Okay, so that's it. That's the electron configuration for hydrogen. Its only electron, which is also its outermost electron, is found in that 1s orbital. Okay, now move to helium. How many electrons does helium have? 2. Right? And helium is still located in the first energy level of our periodic table. The s orbital can hold 2 electrons, so helium's 2 electrons go in the 1s orbital. So that's why helium's electron configuration is 1s2. Okay, its 2 electrons are located in the 1s orbital. Okay, is that kind of making sense a little bit more now? Okay, if we look at lithium, how many electrons does lithium have total? It has 3. It has 3. So lithium's first 2 electrons have to fill these spots, which is where we get 1s2. Okay, then lithium moves down, right? To get to lithium, you have to add an energy level. It has 1 electron located in the s orbital. Okay, so that's where we get 1s2, 2s1. Okay.
Why is helium not in the P?
So helium, because it's in that energy level, it's a noble gas, so it's listed here on the periodic table. But since it only has 2 electrons, it can only be in the s orbital. We can't have an empty s orbital to move on to the p orbital. So really, it should slide over here. Okay? Yeah.
So are you just using the atomic numbers to determine the amount of electrons?
These are all neutral atoms. So the atomic number is the number of protons, and if they're neutral, that means electrons has to equal protons. Okay? Everything in this 2 columns right here are in the S block. Okay? So in each energy level, it has to fill the S orbitals first. So this is like a representation of where it fills the orbitals. Okay? In every electron energy level, it has to fill the S orbitals first, right? Because remember that picture I showed you of the shapes of the orbitals? They have to fill in that order. They fill the S orbitals first, then they fill the p orbitals, then they fill the d orbitals, and then they start over when you move down on the periodic table. So s orbitals get filled first, then p orbitals, then d orbitals. Okay? Yeah?
Why did you move down?
So to get to lithium, we just ran out of elements, so we moved down. Right? So it's just reading across the periodic table. Okay? Because lithium is in the second row, which means it's in the second energy level. So the way the periodic table is set up is to help us determine this. So they go together. Okay? So let's look at nitrogen. Okay, let's look at nitrogen. First thing you do is tell me what block is nitrogen in? The 1s, the 2p, the 3p, the what is it on your periodic table? Just 2p because it's just 1, 2. So nitrogen is in the 2p block. Do we agree with that part? 2p block. So its outermost electron, the last electron that gets added to nitrogen, is in the 2p block. Okay, are we on the same page with that? That means every electron that goes in before the last one just has to fill up all the other orbitals. Okay, so the first electrons that get added to nitrogen, I'll just do it up top here. The first electrons that get added to nitrogen go in the 1s block. And how many electrons does it take to fill an s orbital? Just the s orbital only gets 2, because look, you only have 2 elements right here. Okay, this is a representation. It works hand in hand. Okay, so it takes 2 electrons to fill the s orbitals. Okay, and if you follow along on your pathway, okay, I want you to look at your pathway. We fill the 1s orbitals, then we follow the arrow. What's the next orbital we fill? 2s, and that gets 2. The next orbital we fill is 2p. right, which is right here where nitrogen is, and nitrogen is the 1, 2, third element, so it's 2p3. I really do think they get easier as we just continue to practice, but you need that pathway out and your periodic table out so you can see where they're located and you can see what the order is we need to fill those electrons. Okay? So magnesium, what block is magnesium in? Okay, it's in the S block, and then it's specifically in the 3s block, right? Because magnesium is 1, 2, third level. Okay, so it's in the 3s block. So we have to fill all of our orbitals up until the 3s block. Okay? So you use your pathway and you say, I fill the 1s orbital, it can have 2. Then I fill the 2s orbital, it can have 2. Then I fill the 2p orbital, it can have how many? 6. Then I fill the, what comes after 2p? 3s. And where is magnesium in that 3s block? It's 2. So that's where our 2 comes in. Okay, then to check yourself, you add up these electrons. 2 plus 2 plus 6 plus 2 is 12 electrons. Is that how many electrons magnesium should have? Yeah. So that's it. Okay? That's the electron configuration for magnesium. Okay, is anyone having trouble following along on this? Right, 1s, then you follow it, then you fill 2s, then 2p, then 3s, then 3p, then 4s, right? You just keep following that arrow. Okay, so it's kind of a zigzag along here. Right, you fill the 1s orbital, next is 2s, then 2p, 3s, 3p, 4s. Okay, you follow along that arrow. Okay? It follows your periodic table really closely until you get to the d orbitals, then it gets kind of funky. Okay? And the f orbitals are really funky. Okay. How are you feeling? Potassium's in the 4s block, so we're going to fill everything up to that point. 1s2, 2s, 2, 2p. How many can the p orbitals have? 6. Then after 2p, we move to 3s. It can have 2. After 3s, where do we move to? 3p, right? You're just moving along the periodic table, right? We go from 2s to 2p, then we jump down to 3s, then 3p, so 3p, 6, and then it's in the 4s block. Which one is it? 4s. Potassium is 4s1. There's only one electron in that p block because it's the first one listed. Okay, it's the first one listed, so that means there's only one electron in there. So the way you check yourself is to add up these electrons. 2 plus 2 plus 6, that's 12, 18, 19 electrons. Is that how many potassium should have? Okay, you find that by looking at its atomic number. Oh, I just write electrons like this, so I know it's E negative. That's just how I know it's electron. Yeah. So you can write out the word electrons if you want. I just abbreviate it like that. Okay, the electron configuration. You still want to do a couple of these together? Okay, so copper is located in what block? The D block, and it's not 4, remember, it's 3. They're in the 3D block. So we want to fill everything up until that 3D block. So we can't have empty orbitals before our last electron. We have to fill every orbital up to that point. Okay, so we go 1s2, 2s2, 2p6, right? And you can follow along on your periodic table or using your pathway, whatever you choose. After 2p, we jump down and we say 3s2. Those are full. Then we shuffle over to 3p6. Those are all full. What comes after 3p? 4s. And are both of those electron orbitals full? Yes. And then we move to the D block. So they're labeled 3d. And then how many electrons are found in that D block for copper? What do we think? 9. Yeah. You count over to copper. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's got 9 electrons located in that d orbital. Okay, and we just found that by counting over, starting at the d block, which is the transition metals, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where that 9 came from.
So how do you know how do you know how far to go?
I want you to do silicon on your own, and I want you to do bromine on your own. Silicon and bromine. Do those two on your own. Raise your hand if you have questions as you're going. Anissa, do you want to read me your electron configuration for silicon?
1s2, 2s2, 2p6, 3s2, and
3p2. Perfect. 3p2. Okay. Perfect, perfect. Joe, do you want to give me the electron configuration for bromine?
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p10, 4p5.
4p5. Perfect. In the perfect order, right? We go 4s, then we fill 3d, then we go 4p5. So we are following exactly along on our periodic table. We just know those d orbitals, instead of being 4d, are 3d. Then we move over to 4p. It's the 5th element, so 1, 2, 3, 4, 5. That's where our 4p5 comes from. Perfect. Okay, so what happens if I ask you to identify an element based on the electron configuration? What do you look at? Yeah. Yeah, that would work. That would work. A quicker way would be to look just at the last, that. 4p5 means we look 1, 2, 3, 4. We're here in the p block. 1, 2, 3, 4, 5 is bromine. So you can do it either way. You can add up the total number of electrons, or you can look just at the last kind of, portion of that electron configuration to determine the element. Okay, so if I had an electron configuration that looked like this, 1s2, 2s2, 2p4, what element am I talking about?
Right?
2p4. Oxygen. 2p4 means I'm in the second level. So even though on our p block, right, there's no 1p. Did you notice that? There's no 1p block, because there's not p elements here, except, remember, helium really goes over here. So 2p means second level 4. 1, 2, 3, 4. So I'm talking about oxygen. Okay? Now I'm going to show you how to make this process even easier. We're going to do something with abbreviated electron configurations. Abbreviating electron configurations. We can do that with a noble gas. Okay, we're going to abbreviate using the noble gas ahead of that element. Okay, so remind me where the noble gases are on the periodic table. Group what? (18). Noble gases are group 18. Helium, neon, argon, krypton, xenon, radon. Right, those are the noble gases. And what's special about the noble gases in terms of their electron shells? What would be special about the noble gases in terms of their shells? Right? What do we know about their valence electrons? Those are outer electrons. They're full. They're full. Their electron shells are totally full. First energy level for helium, the 1s orbitals, they're full. 1s2, right? For neon, we'd go 1s2, 2s2, 2p6. That orbital is full, right? So the noble gases all have full electron shells, which is why we can abbreviate with them. Okay, so this is what calcium looks like. A regular electron configuration for calcium looks like this. 1s2, 2s2, 2p6, 3, S2, 3p6, 4s2, right? That's what calcium looks like. It's in the 4s block. It's the second element. Do we agree with that? Okay, so if I wanted to abbreviate calcium's electron configuration, I look for the noble gas that comes before calcium. So look at your periodic table. What is it? The noble gas that comes right before calcium is argon. Okay, so the way we abbreviate is we say calcium's electron configuration is the same as argon plus 4s2. Okay, so that's how we abbreviate it. We say it looks exactly the same as argon, right? Because argon's electron configuration, if we wrote out argon's configuration, 1s2, 2s2, 2p6, 3s2, 3p6, right? That's what argon's configuration is. These two look exactly the same up to that point, right? Do we agree? Those two look exactly the same. So the way we abbreviate it is we say our noble gas of argon plus whatever comes after that to get to that element. Okay? You only can abbreviate with noble gases. You can't abbreviate if your s orbitals are full, right? You can't abbreviate with calcium plus something else. Right? You abbreviate with with the noble gases only. Okay? Yeah. Okay, so platinum is number 78. It's in what block? It's in the D block, and it's the 3D, 4D, 5D block, right? Do you agree with that? 5D, okay? Which means, what's the noble gas that comes before that? Xenon. So I put that in brackets, xenon. Then, after xenon comes what? Okay, so let's count. After xenon comes cesium, right? So 1, 2, 3, 4, 5, 6s. 6s2. And we want to go to 5d. So in order to get to 5d, we say 4f, because that's what comes next on our pathway. So these lanthanides and actinides get shoved up in there. Okay, how many electrons can the F block hold? They hold 14. So although on your periodic table, lanthanum and actin, they really should go up here. Okay, they hold 14. F block holds 14. So 4F 14 plus 5D what? Count lanthanum. 1, 2, 3, 4, 5, 6, 7, 8. 5D8. So that's platinum. Okay. Abbreviated configurations, I want you to try iron and strontium. D6. Perfect. 4s2, 3d6. So it's the same as argon plus 4s2, 3d6. That's what our abbreviated version tells us. Okay, and strontium. Natalie, do you want to give us strontium?
Krypton with the brackets, 5s squared.
5s2. Perfect. Okay, strontium is the second element in that S block, which means its 2 outer electrons are in that S.